So I've printed out a periodic table so that I can demonstrate to you how to calculate the charge on an ion. So at the moment, looking at this periodic table, we can see all of our different elements ranging from group 1 all the way through to group 18 at the other end. All the elements that you can see on the periodic table are currently neutral. That means that they don't have a charge. The reason for that is that all of the elements on the periodic table have the same number of positively charged protons and negatively charged electrons. If we look at oxygen, for example, oxygen has an atomic number of 8. That means that it has 8 positive protons and 8 negative electrons. Having 8 positive and 8 negative cancels out, so it gives the oxygen atom an overall charge of 0. Okay. However, in chemistry, being neutral and being stable are not the same thing. An element that is stable will not react with any other element, not even atoms of the same element. To be stable, an element must have a full outer shell of electrons. The only elements on the periodic table that are currently stable are all of these elements in group 18. And the reason for that is because they already have a full outer shell of electrons. Helium has 1 electron shell, and that 1 electron shell is full with its 2 electrons. All the other elements in group 18 have 8 electrons in their final shell, so they are already full. That means that all of the elements in this group here, group 18, are stable. They are unreactive. So if you put them with another element in a chemical reaction, nothing will happen. All of these other elements between groups 1 and 17, though, are unstable, and that's because their final shell of electrons is not full. We can tell how many electrons an element has in its final shell by looking at the group number at the top of the column. So if we look at group 1, all the elements in this group will have 1 valence electron in their final shell. Valence electron is the word we use to describe the electrons in the final shell. So I'm just going to make a note here. 1 valence electron. And following that pattern, all the elements in group 2 have 2 valence electrons. Now here's where the pattern gets weird. We skip over all of these elements in the center. These elements are called transition metals. We skip over them because they can actually do a whole range of different things, and they can form ions with multiple different charges. So we're just going to ignore them for a minute, and we're going to jump over to group 13. If we look at group 13, we look at the second number, and all the elements in groups 13 have 3 electrons in the final shell. Group 14 have 4, group 15 have 5, 16 have 6, 17 have 7, and we can look at group 18. There's a little exception to the rule here. Most of them have 8 in their final shell, as the number 18 would suggest, except for helium, which is the exception. It's so small, it only has 2. So, the reason we're talking about number of valence electrons is because in order for an element to be stable, it must have a full outer shell. That means it must have 8 electrons in its final shell, with the exception of hydrogen and helium, which only need 2. So, all of these elements in group 1, with their 1 electron in their final shell, they have an option. They can either get rid of that 1 electron, and they can go back to their last full shell, the previous shell before their outer one. Or they could pick up 7 more electrons and try and fill up that outer shell to 8. But because atoms are super lazy, they will actually take the easiest option, the one that requires the least amount of energy. So as stated on your worksheet, elements with 3 or less valence electrons will tend to get rid of them. It takes less energy to get rid of those electrons instead of trying to add more into their final shell. If we picture a lithium atom, for example, here's the nucleus of the lithium atom. In the first shell, we have 2 electrons. And in the final shell, we have this one pesky electron, as we can see written here. Now, like I was just saying, it is easier for lithium to get rid of this electron and pretend that this inner electron shell is the final and only shell that it has. And this inner electron shell is full with its 2 electrons. Now, when you get rid of something that is negative, and I've been teaching the students that we can use an emotional analogy for this. When you get rid of negative things from your life, you tend to feel more positive. And the same goes for these atoms or elements. When they get rid of these negatively charged electrons, they become positive. So we know that the name for an atom that gains or loses electrons is an ion. And so an ion that has gotten rid of an electron will have a positive charge. So all of these elements in group 1 that are getting rid of 1 negative electron will end up with a charge of 1 positive. Now, all these elements in groups 2, they have 2 electrons that they need to get rid of in their outer shell. Again, getting rid of 2 negative things will give all of these elements a charge of 2 positive. We're going to skip over the transition metals again, and I'll come back to them in a tick. All of these elements in group 13, they have 3 electrons in their final shell. It's still easier to get rid of 3 electrons instead of trying to pick up another 5 in order to fill up their shell to 8. So if we get rid of 3 negative electrons, all of these elements will get a charge of 3 positive when they become ions. Elements in group 14, because 4 is halfway to 8, they can actually go either way. So these elements can either form ions with charges of 4 positive, or if they decide to pick up 4 electrons to fill up their shell, gaining 4 negative things will give them a charge of 4 negative. Elements in groups 15, they have 5 valence electrons. So now the tables have tipped, because having 5 electrons, they've got a choice of getting rid of those 5 or picking up 3 more in order to fill up their outer shell. In this case, it's easier to gain 3 instead of get rid of those 5. So when you pick up 3 negative things, or when you gain negative things in your life, you tend to feel more negative. So gaining 3 negative things will give these elements a charge of 3 negative. Elements in group 16 with their 6 valence electrons, they can get rid of 6 or they can pick up 2. It's easier for them to pick up 2 negative electrons, so they will get a charge of 2 negative. And elements in group 17, they have 7 valence electrons. It's easier for them to pick up 1 more electron to fill up their shell than to try and get rid of those 7 electrons they already have. So they will get a charge of 1 negative. Group 18 elements, because they are already stable, they're not going to do anything. They actually don't form ions, they just exist how they are. When we write the symbol for an ion, we need to write the same symbol that we can see on the periodic table, but then we need to add the charge above it to show that it is a charged ion that has gained or lost electrons. So if I was to say write the ion symbol for magnesium, magnesium is over here in group 2. It has 12 electrons in total, 2 in the final shell. It's going to get rid of those 2 electrons, so it will form a positive ion with a charge of 2+, and I would write that symbol like this. Capital M, lowercase g, with the 2+ up above it. Okay, it's really important that we write that charge as superscript because when we start writing these numbers differently in chemistry, it can mean different things. Now, I want to come back to these transition metals for a second. Transition metals will always form positive ions because they are metals. Generally, the rule is anything that is a metal, so on the left-hand side of the periodic table will form positive ions, and these non-metals in the top right-hand side will form negative ions. So these transition metals will form positive ions, but they can actually form various ions. Iron, for example, can form 2 positive ions or 3 positive ions or 1 positive ions. So the only way to know which one that you're dealing with is when the element symbol is written, we actually write in Roman numerals afterwards the charge of that ion. So if I was using iron in an experiment, it would say something like this. And then in Roman numerals afterwards, it would have brackets and it might have a 2. So this is Roman numerals for the number 2. This means that I'm dealing with an iron 2 positive solution. Another one that you might deal with is copper. So copper, again, Roman numerals, you might see 3. That means that you're dealing with a copper 3 positive ion. Okay, and it can go all the way up to 4. So an example of one that forms a 4 positive ion is lead, and it will look like this. So no need to try and use the group numbers to figure out the ionic charge on these transition metals because that rule doesn't really apply to them. Simply look for the Roman numerals in the brackets afterwards and it will tell you the charge that you need to place on the ion.